Good morning and good afternoon, everyone. Thank you for joining the Upstream Technology Leadership webinar today. My name is Berenice Aldaz, and I am part of the technical marketing team for drilling software in Schlumberger, and I will be host for this webinar. Today's webinar will be presented by Brandon Foster, and will cover physics-based drilling engineering. Brandon graduated with a Bachelor of Petroleum Engineering from Montana Tech on the University of Montana. He has 17 years in the industry, where he has worked as a drill engineer for Mobil, ExxonMobil, Pure Resources, and K&M Technology Group. In the past 13 years at K&M, he has held various engineering and management positions where he has supported and delivered some of the most challenging roles in the world. In his current role as Technology Development Manager, he is responsible for the technical evolution of the company's ERA drilling engineering software, modeling techniques, and technical philosophies. Before I hand over to Brandon, please be aware you can submit your questions using the green button on the left, which we will aim to answer at the end of the presentation. With this, I'll hand over to Brandon.
Thank you so much, Bernice, and good morning, good afternoon, and good evening to those of you joining us around the world. I'll share with you a quick outline of what we plan to talk about today. I'd like to start with a bit of a history of what the role of a drilling engineer used to be, what it is today, and what we think it could be going forward in the future. And then I have 3 real-world examples from U.S. land where we use some of the techniques that we're talking about to improve drilling performance in different ways, drilling faster, improving cement jobs, and potentially preventing drill string failure. And then we'll wrap up with a proposition for managers, engineers, and educators. Over the last 150 years, technology for drilling has evolved, starting with Colonel Drake's famous well that was drilled with a cable tool back in the 1800s. When rotary rigs and rotary drilling were introduced, spindle top was a significant improvement over Colonel Drake's technology. And then in the early 1900s, oil-based mud and tricone bits were another significant step change that allowed us to drill faster and further. When PDC bits were introduced in the 1970s, again, another step change in drilling performance was attained. And then by the end of the 20th century and beginning of the 21st century, we began to use technology such as rotary steerable systems and wired drill pipe. From a drilling engineering standpoint, there was a 50-year period that I like to consider the golden age between 1950 and around 1990, where drilling engineers such as Arthur Levinsky and other famous folks really dove deep into the physics of what was happening below the rotary cable and gave us a much better ability to predict and understand the physics of what was happening downhole. In 2016, the role of a modern drilling engineer tends to revolve more around paperwork and meetings than it does investigating and understanding the physics that Arthur Levinsky and those other famous forefathers were really striving to understand in their careers. What we believe the role of a drilling engineer could and should be is more analogous to that period of time in the golden age that I referred to, where drilling engineers spend most of their time doing technical analysis, evaluating torque and drag and casing design and geomechanics and drill string design to truly understand and optimize the design of the well and then put into place good practices while the well is being executed. Part of that process involves systematic redesign from well to well so that we're constantly improving and changing what needs to be changed to allow better performance. There was an interesting paper that was written by one of my former colleagues at Mobil. Dave Herrick had published a paper in 2002 called The Fivefold Way, methodology, The Fivefold Way. And it didn't necessarily dive into drilling engineering like I'm going to in this presentation, but it talked about different approaches that humans can use to solve problems. And what Herrick called the medicine approach, or what I like to call closeology, other people may call it the empirical method, is where you have a mass of data, but you don't have a model that describes the physical problem or the issue that you're trying to solve. And the reason why he called this medicine is a good example is the pharmaceutical industry, where early on, pharmaceutical companies didn't have a deep understanding of the human body, but through trial and error and a lot of experimentation, they amassed data that allowed them to pin down what drugs and what chemicals would have a positive effect for certain types of symptoms, certain types of diseases. So it was a very data-driven problem-solving process, and it was effective for many people. Not 100% effective, obviously, but The statistics were certainly with them when they were trying to solve and prevent certain types of diseases. Now, the other method that Herrick mentions, he calls religion. I'd call it opinioneering. But in this approach, you've got a model, you've got a theory or a hypothesis, or maybe it's an equation, or maybe it's a computer program, but you don't have data to back up and verify the validity of your model. So you're really kind of leaning on faith that your model is the correct model and that it's properly describing the problem that you're trying to solve. Now, what Herrick goes on to explain is that his preferred approach, and certainly what's advocated in the paper, is the scientific method, where we have a theory or a hypothesis or a computer program or an equation, and then we go out and we do an experiment or we collect data that either confirms or invalidates our original hypothesis or theory or equation. And as we collect more data and we feed that back into the model, we are given the opportunity to further improve the model's ability to predict or solve the problem that we're attempting to address. So it takes both data and a model to really get a deep understanding of the issue that we're trying to solve. And my timing couldn't be more perfect, but on the morning after a tumultuous election, the last method, and this was Herrick's least favorite problem-solving approach, is what he calls politics, where we're purely motivated by self-interest. We don't look at data, we don't have a model, we simply make decisions based on what's best for us at a given point in time. So take, for example, selecting a drill bit. You could choose a drill bit to drill in an area using any one of those approaches. Perhaps you have a computer program that says bit A drills faster than bit B, or perhaps you have a bunch of data that says that bit A drilled faster in this offset field than bit B. Or maybe perhaps you run bit A because your boss or your manager really wants you to run that particular bit. That would be an example of politics. What we'd like to do is gravitate towards science, where we have a prediction, a way to predict what the performance will be, and then we collect data from the field and we confirm whether or not that model is an accurate prediction. As we said, each one of these methods is present in daily life, and it's important to get an understanding which method any particular individual that you're working with is using at any given point in time. And what Herrick encourages us to do is move and migrate towards science. It gives us a deeper understanding of what's going on. And really, if you think about it, the laws of physics that we live by were understood and derived from the scientific process. One of the things that we battle when we try to use this scientific approach is the general psychology of a driller. And I really could say it's the psychology of a human being, because it's not unique just to drillers. And when I say driller, I don't mean necessarily the individual that's on the brake handle. I'd consider myself a driller. Obviously, I don't work on the rig floor running the rig. But people that are in the drilling organization, they tend to be skeptical folks. I'm a skeptical person. Whenever you hear about a new technology or a new technique, you tend to look at it with a bit of a jaundiced eye and say, okay, is this really going to deliver as advertised? Drillers also tend to rely quite heavily on their previous experience. We're always thinking about the last well that we drilled or the last 10 wells that we drilled, and that's what tends to guide our decision-making process as we go forward and we plan our next well. Sometimes that experience is applicable and quite useful, and other times that experience can actually be more of a liability or a detriment if the well or the project that we're about to go embark on is significantly different than what we just got done doing. Drillers in general tend to use medicine and politics, quote unquote, a lot on the rig. We use our previous experience quite a lot, so that's the empirical method, the medicine approach, and politics are just a natural part of daily life, and they're certainly present on a rig floor, just like everywhere else. The other aspect that's difficult, not just for drillers, but for any human being, is that it's hard for our brains to process and anticipate the changes when we're dealing with a nonlinear system. And to illustrate that point, I've got a graph here, and I've plotted some data on the x-axis and the y-axis. And if these were my data points, what most mechanically minded individuals, so engineers and people that are involved with drilling, most of us, I don't want to speak for everyone, but most of us would imagine a straight line drawn through those points. That's certainly the trend that we're on. That's where the data is pointing us towards. So if we were trying to anticipate something that was going to happen in the future out there at the 7 or 8 or 9 territory on the x-axis, our minds would kind of draw us in that linear direction. But if I told you that the data that we were collecting was coming from a leak-off test, we all know that we can't pressure up on rock during a leak-off test to an infinite pressure. At some point, that pressure is going to fracture the rock, and we begin injecting mud into the formation, and we flatline our pressure development. No matter how much volume we pump, the pressure doesn't increase. So we need a physical model that's going to predict and allow us to anticipate where that point is. Because our previous experience, those first 10 data points, don't do a good job of allowing us to predict what's going to happen later on down the road in the future. And that sort of phenomenon is very common in drilling operations, whether you want to talk about hole cleaning or torque and drag, buckling, ECDs, really the vast swath of different physical phenomena that happen when we drill wells have an element of this nonlinear behavior. So data's good, but we need a model to go with it so that we can anticipate when those changes occur. So I'd like to move on to our three examples. The first example is, and all examples are from U.S. land, and this one happens to be in northern Louisiana in a particularly deep, hot environment. So pretty high bottom hole pressure, high mud weights, oil-based mud, over 300 degrees Fahrenheit, approaching 320, 330 degrees Fahrenheit. And the main challenge that this operator is facing is they're drilling 6.5 or 6 3/4 inch hole in the reservoir, and they've experienced quite poor ROP and unpredictable directional response, which is leading them to have to make multiple trips out of the hole with the BHA and back in again when the BHA doesn't perform as expected. But the ROP is really the big overriding issue. And what was used for this particular project to improve performance was a concept called mechanical specific energy, or MSE for short. And many people in the industry are starting to use this technique. For those of you that aren't familiar, it is a relatively simple equation where we sum the sources of energy that are going into the drilling process, and then we divide by the volume of rock that's being destroyed over a certain amount of time. So we need to know the weight on the bit, the RPM at the bit, and the torque at the bit, and then obviously the rate of penetration we're drilling at. The difficulty in using this technique for directional wells, though, is that we very rarely measure the weight at the bit and the torque at the bit. What I'm going to show you in a minute is where we've used a computer simulation to transform surface weight on bit, surface torque, surface RPM into downhole values. And when we've converted this into a downhole parameter, that gives us a better, deeper understanding of what's happening at the bit face and allows us to determine whether or not we're drilling efficiently or not. Now, when this technique was developed, what the original authors discovered is that the mechanical specific energy, when we're drilling efficiently, tends to conform fairly closely to the rock strength. There is an efficiency factor that goes into this equation, but with the correct efficiency factor, what we find is MSE should parallel our rock strength. Now, interestingly enough, this technique was developed in the mining industry in the 60s, and it really didn't get noticed in the oil and gas industry until the early 90s. And even though there were papers that came out and said, hey, yeah, this is good stuff, we could use this, it really didn't become popular until the early 2000s. And a lot of people credit Fred DePriest at ExxonMobil with a quite famous paper where he was able to demonstrate the performance that was observed by using this technique in real time on a variety of different wells. So that certainly got folks' attention, and people started paying more credence to what this technique can offer. Now, what most people tend to do is use mechanical specific energy in real time while they're on bottom drilling, trying to optimize the weight on bit and RPM that's applied, and flow rate potentially as well, to maximize drilling performance. But what we really believe is the greater opportunity for mechanical specific energy is to use it in planning mode, to look back on the last well you drilled and then forecast what is it that's inhibiting you from drilling faster. Where are the bottlenecks? Where are the things that you could change that would allow you to drill faster on the next well? The changes might be bit selection, the changes might be drilling parameters, they might be BHA design, it might be hole sizes and drill pipe sizes. You really have to be quite open-minded in the planning phase to ask yourself, what could I do different in order to drill faster? Now, to look at this specific example that we're talking about, what I've plotted here is the very first well in the program for this operator. We've got bit depth on the y-axis and then the average rate of penetration that they were achieving on the x-axis. And you can see that they were drilling fairly consistently at 20 to 25 foot an hour, and occasionally we'd get drilling breaks up to 50 foot an hour, but overall that's a typical ROP. And that's the same sort of ROP that was being reported by other operators in the area. So everybody was having quite similar experience. When we go back and calculate the downhole mechanical specific energy, so not the surface MSE, but the downhole MSE, what we find is it's taking 150 to 100,000 PSI of specific energy input to drill at this rate of penetration. And if you recall, I mentioned earlier that MSE should be much closer to rock strength. And we're able to predict and calculate rock strength either through core testing or through log interpretation. And both the logs and the core testing suggest that this rock is not nearly that hard. In fact, it's on the order of 10 to 12,000 psi compressive strength. So we're drilling extremely inefficiently. If we were drilling efficiently, the expectation would be that we should be drilling at 100 or more foot an hour, and obviously we're not. So the question is, what is it that's causing us to be so inefficient? Well, through more detailed analysis at the MSE, what we concluded is that bit balling was the thing that was preventing us from drilling faster. And that was met with a lot of disbelief and skepticism, because there is a pervasive attitude that you can't ball up a PDC bit in oil-based mud. And in fact, it turns out that this problem was solved quite a while ago in a DAA project where several companies had determined that it is possible to have balling with oil-based mud if the conditions were right. And this play was the sort of environment that make the conditions right for bit balling. Now, why it was happening is because we really weren't choosing bits and focusing in on the right things to prevent balling in the first place. Because everybody's perception was that this was a hard rock area. We tend to run 7 or 8 blade heavy set bits with small cutters and lots of back rake. We wouldn't really focus on hydraulics. A lot of people would run wide open nozzles on their bits. And generally we were using low speed, high torque motors, which that's the exact opposite direction we should be going if bit balling is our main concern. So what we gravitated towards was, rather than heavy set bits and very conservative parameters, we moved towards much more aggressive parameters, spinning the bit faster, much better bit hydraulics, much more aggressive bits, so 5 blade instead of 7 or 8 blade, big cutters, very little back rake, very little chamfer on the cutters. We started limiting the weight on bit that was being applied so that we could control our depth of cut and not take too big of a bite of this soft shale, which would in turn potentially ball up the nozzles or the water courses. Another major change that took place after this kind of aha moment that bit balling is what we were dealing with is, rather than using standard elastomer, low-speed, high-torque motors, we moved towards even rubber thickness, medium-speed motors. So rather than a 7/8, we're moving more in the neighborhood of a 4/5 lobe configuration, and that allows us to drill and deliver much higher horsepower at the bit, and it allows us to operate at much higher differential pressure. Higher horsepower, when we're drilling efficiently, translates directly into ROP. So the first key is we have to drill efficiently, which is where the bit design comes into play. The other thing that was changed in order to eliminate the unnecessary trips is, rather than the traditional BHA design of a big bent housing, so by big I would mean 212, 238, somewhere in that neighborhood, a big bent housing setting with no stabilization, we migrated and moved towards lower bend setting motors with stabilization. Now, we didn't change the build rates that were designed into the well path. All the wells were averaging somewhere around 9 degrees per 100 foot in order to go from kickoff point to the landing point. The blue curve on this graph shows the well path inclination on the x-axis and the dogleg severity on the y-axis. And you can see with the big bent housing slick BHA approach in blue that the BHA is underperforming initially, and then it dramatically overperforms somewhere around 30 degrees inclination. And then we have to pull out of the hole and dial the motor back down so that we're not continuing to drill with these excessive doglegs, which was a consistent case for many rigs in the area, and actually a very common observation for many rigs and operations in U.S. land. Slick, unstabilized, big bent housing motors yield this sort of behavior. Now, the red curve shows the sort of doglegs that were achieved with a stabilized 1.5 bend motor, and you can see that we get much more consistent dogleg response, and we're right in the neighborhood of our planned well path. So what that allows us to do is to drill from kickoff point all the way to TD with one bit and one motor, whereas the other approach was requiring multiple bit trips not only in the curve but also in the lateral, and it prohibited us from being able to rotate the drill string fast enough for efficient hole cleaning. Now, in order for the stabilized assemblies to work, a detail that often gets overlooked is we redesigned the stabilizers that were used. Common off-the-shelf stabilizers tend to have too long of a gauge pad length to allow slide drilling to happen. The stabilizers end up jamming into the high side of the hole. So looking at the jamming angle and what was required to allow the stabilizers to slide when the directional driller was orienting the string, the gauge pad length had to be dramatically reduced to somewhere in the order of 3 to 4 inches as opposed to the standard 12 to 18-inch gauge pad length. We went from directional drillers being very hesitant and very skeptical about running stabilizers because their previous experience said stabilizers don't work, to, by the end of the program, the directional drillers were absolutely mandating and screaming for, yes, I need to have a stabilized assembly because it made their life so much easier. The BHAs were predictable, sliding was easier, everything was easier when we had BHAs in the hole that would do what they're supposed to do, and it was predictable. Now, if we go back to our original ROP and our MSE, when we were drilling with the original combination of parameters, thinking that the rock was hard, this was our ROP and our energy input. When we eventually got all these pieces put together over the course of several wells, we were consistently drilling at 100 to 125 foot an hour, and now our mechanical specific energy is falling directly in line with the rock strength that we had predicted. So physics and reality, they're both starting to converge here. We have a model that says this is what should happen, and then we have actual measurements that say, yes, this is indeed what is happening. So big improvement for the operator, 5-fold increase in ROP. And what that meant over the life of the program, the operator had 14 wells to drill. The first well in the program, in chronological order here, it took 10 days per 1,000 feet to drill from the kickoff point to TD. And so we've tried to normalize for lateral length since each well had a little bit different lateral length. You can see that the learning curve shows us consistently improving up until the point of about the 9th well where we reach an asymptote. But a 5,000-foot lateral was originally taking 50 days, and by the 9th well, we were drilling it in 5 days with no unplanned trips, with high ROP and consistent behavior. Great example, tremendous cost savings, saved over 400 days of rig time and $30 million by improving very aggressively. This is a very steep learning curve, and the team did a tremendous job. The $30 million savings doesn't include all of the accelerated production and the benefits that we get by compressing the rig schedule. So that's just purely rig time alone. Very successful project using a little bit of physics to improve performance. The next example I'd like to talk about, it's in a similar area, but it's a different type of problem that we're trying to solve. So in this case, the operators drilled a lot of 5,000-foot laterals. They figured out many of the things that we've talked about in the last example. This was much later in the chronology of developing in this field. But the standard program was 10 3/4 surface casing, 7 5/8 intermediate casing above the kickoff point, and then drilling a 6 3/4 inch hole to TD and running a tapered 5.5 by 4.5 casing string. What this operator wanted to know is what would change if I went from drilling 5,000-foot laterals to 11,000-foot laterals. I feel pretty good about how we drill 5,000-foot laterals, but I've never done an 11,000-footer. What would need to change? Can we actually get casing to bottom? Can we get it cemented? Those were the things that were bothering the operator. So the first thing that we need to evaluate or determine before we can decide if any changes are necessary is to look at what happens during cement placement. Because the whole purpose of drilling this well is to be able to get oil and gas out of the ground, and the necessary element to getting oil and gas out of the ground is to properly stimulate the rock. And we can't do that unless we've isolated in the lateral. So what I'm showing here is the depth of the well, measured depth on the y-axis, and equivalent mud weight on the x-axis. On the left-hand side of the graph, we've got pore pressure in black, and then 3 shaded areas which represent the collapse gradient or wellbore stability threshold for different levels of damage that would occur to the side of the borehole. So we don't want our equivalent mud weight to drop into any of those shaded regions. And that explains why our equivalent static density, which is this pink curve in the middle, is above each of those shaded regions. Then on the right-hand side of the graph, we've got 5 different curves that all parallel each other, and what they represent is the equivalent circulating density at the end of the cement job with mud and cement in the annulus for different displacement rates. So the blue curve represents low rate displacement, the purple curve on the far right represents high rate displacement, and certainly for cement placement and mud removal efficiency, we prefer to be displacing at a high rate, not at a low rate. Even at a low rate of displacement, though, what we find is the ECD is going to exceed both the minimum horizontal stress, which is represented by the gray shaded area, and the fracture initiation pressure, which is defined by the black shaded area. So this is an inoperable well design because we can't place cement without losing returns. And if we lose returns during the cement job, particularly at the bottom of the hole, as this model predicts, then we're not able to achieve our design top of cement, and we don't have isolation across the entire lateral, which compromises our ability to stimulate effectively. So we need to solve this problem. And the solution that we gravitated towards was upsizing the wellbore, going from 7 5/8 intermediate to 9 5/8 intermediate, and running the same 5.5 casing into an 8.5 inch hole rather than a 6 3/4 inch hole. And when we rerun the ECD simulation at the end of the cement job for a wide range of different flow rates during displacement, you can see that the ECD, these colored curves in the middle, are now well centered in our mud weight window. We have lots of freedom to go up or down on our mud weight or our displacement rate without risking collapse of the borehole or initiating fractures and losses. So this was the solution that the operator gravitated towards because their number one priority was being able to get a good cement job on this long casing string. Now, just because we've got a successful cement job doesn't mean that this is all going to work. The first thing that we have to do is get the casing to bottom. First prerequisite, casing has to go to bottom. So if we look at a simulation here of the drag as I'm running the casing in the hole, on the y-axis we've got the depth, I'd say bit depth, but what I really mean is the bottom of the production casing, all the way to almost 25,000 feet. And then on the x-axis is the surface hook load, so what we read on the weight indicator. The red curves represent what it would look like if we were pulling out of the hole, which we don't intend to do. And the blue curves on the left, which are more important, is what we would see when we're running in the hole. For different levels of friction, low levels of friction here on the right and high levels of friction on the left, what this simulation tells us is that for medium to high levels of friction, which is normal in this area, the casing is not going to go to bottom. It will stop due to drag and buckling of the casing, and that's unacceptable because the whole purpose of drilling this long lateral is to get casing to bottom. So this isn't going to work, unfortunately. To solve that problem, a very effective solution is to rotate or ream the casing into the wellbore. So now what we're looking at on the left is a very similar simulation to what we just went through, only now what I'm doing is combining running in the hole or out of the hole with rotation. And you can see when we rotate, what we're able to do is transfer axial friction into torsional friction. Your drag goes down and your torque goes up when you ream in the hole. On the right-hand side, this simulation shows the surface torque that I would see for different levels of friction compared to my torsional limit. So the light blue shaded area is the torsional limit of my connections, and the vertical blue and the vertical red lines represent the torsional limits of the top drive. Now, in order to make this work, we need to have quite high torque connections on the casing, which fortunately the operator had in inventory. So this was the preferred solution to overcome these challenges. Simply ream the casing in the hole. If it was different circumstances, it may mean that we would have to recut connections and upgrade the torsional capacity. Fortunately, the operator already had quite strong connections in inventory. Now, as I said before, we really like to gravitate towards this scientific method where we have a model or a simulation, and then we verify and validate with actual data. So here we've run casing into this wellbore, and we've overlaid the actual observed hook load on the left and the actual observed torque on the right as we're reaming the casing in the hole. And beneath those actual measured data points in black, we've got simulations in the background. So we've simulated the hook load, simulated the torque, and you can see that theory and reality agree quite nicely with each other, which gives us confidence that we do have a good understanding of the physics that's happening in this well, and it's therefore a valid model for predicting and forecasting what will happen on future wells. The end of the story is the operator was able to get casing to bottom, they were able to get a good cement job, and the well became an effective producer, which is exactly what we wanted to have happen. But it wasn't without significant change. We had to fundamentally change the architecture of the well in order for that to happen, which is not something that's easy to do at the last minute. This was all thought through and planned many months in advance, not just weeks before spud, as is often the case. Last example I'd like to show is not quite as sweet of a story as the last two. This was a missed opportunity. It was a situation where the operator was drilling fairly hard rock in East Texas. It's a small hole, 6 1/8 inch hole, 4-inch drill pipe, and water-based mud. Unfortunately, they twisted off the drill string while drilling this well and were unable to fish. And because they lost the string in the hole and had to re-drill the lateral, that was a significant expense and lost in hole cost, both the cost of the BHA and having to re-drill the lateral. The root cause of why it happened is because the hole was over gauge, and the weight on bit that was being used produced such extreme buckling that the stress in the string exceeded the fatigue endurance limit of the drill pipe. And we ultimately fatigued the drill pipe until failure. All of this could have been identified and prevented had the well been monitored in real time. This was all looked at after the fact, and it certainly could have been prevented if the techniques that I'm about to show you were done in real time. So we originally got the call from the operator because they were complaining of high torque. And so the first thing we looked at was the off-bottom torque. So whenever we rotate the drill string before the bit goes to bottom, we have an opportunity to measure the torque generated by the string and compare that to our simulated or predicted values. So we have a model that predicts what the string-generated torque should be. So we've got our bit depth on the y-axis and the torque that's observed or predicted on the x-axis. The black is the measurements, and the colored curves represent the simulation. And what we conclude from this analysis is that there was really nothing alarming or unusual about what we were seeing. The observed torque was consistent with expectations and consistent with predictions. However, while on bottom drilling, we see a different story. So this is also bit depth on the y-axis and torque on the x-axis, but now what I'm looking at is the on bottom torque. So once the bit's on bottom and I'm drilling ahead, what torque do I see at surface? Now initially the torque was low and acceptable, but as we drill further out on the lateral, the torque increases, which in and of itself is not a problem. But as we get close to TD, the torque is reaching the maximum makeup torque limit of the drill pipe. And the operator felt concerned that 20,000 foot-pounds seemed like an awful lot of torque in a 6 1/8 inch hole with 4-inch pipe. What we did is went back to the model and said, okay, let's simulate what our on-bottom drilling torque should be. We don't know exactly how much torque is being contributed by the bit, so let's just simulate the drill string's contribution. So the black curve is simulated drill string generated torque with the drilling parameters that were being used. And what we do is we use the difference between the red curve and the black curve, just simple subtraction, to infer what the bit generated torque should be. Now, this isn't a measurement of bit torque, it's an inference of bit torque. And what you expect to see is that the bit contribution should be fairly consistent as we drill the lateral if our formations aren't changing dramatically and if we're not using dramatically different drilling parameters. Now, we did have some small lithology changes, but the thing that's alarming here in this well is that the bit torque was consistent initially, and then it starts increasing from about 14,500 feet onwards. Now, fortunately, this was an area where we had two different ways of inferring bit torque. I just mentioned that we ran a torque and drag simulation to capture this blue curve, but the other method that we can use is the motor performance. The positive displacement motor was used on this project, and every positive displacement motor has a relationship between differential pressure and torque. So we know what the observed differential pressure was, and we can convert that into inferred bit torque. And what you hope to see is that green curve, our differential pressure-derived bit torque, to agree nicely with our blue curve, our torque and drag inferred bit torque. And you can see that that generally is the case down to about 14,500 feet. And then all of a sudden we start to see this rapid divergence between the two different methods of calculating bit torque. And if I was to zoom in and look just at those two curves and try to remove the distraction of everything else and overlay my gamma ray, you can see on the gamma ray that initially when I was drilling the lateral, I was in a clean sand, and then I entered into a shaley interval, and then back into a clean sand. And it was after getting back into the clean sand that we started seeing the separation and divergence between the blue and the green curve. So a lot of different hypotheses and theories were thrown out, and one of the theories was, well, what if the hole was over gauge? What if in those shale layers our water-based mud is not adequately inhibitive and the shales are enlarging over time because the water is able to penetrate the shale and the hole washes out? Well, if the hole was to wash out, and to wash out quite severely to 20 inches, then the simulated bit-generated torque would look quite different. Because now with a large washout, the torque and drag simulation is detecting that there's severe buckling going on in the washout. That severe buckling is contributing and creating much higher torque in the drill string. And of course, when the drill string creates more torque, that leaves very little left to the imagination for what the bit could be contributing. And now we see a very good comparison between the two different methods for calculating bit torque, which suggests that our hypothesis may indeed be correct. Now, unfortunately, they did end up twisting off when they were drilling this interval, And the movie that I'm playing right now shows why. So 3 different graphs played in real time as we're drilling this horizontal interval: tension, torque, and then on the right, bending stress. Whenever the bending stress, the black curve, starts to get into that gray shaded area on the right-hand side of the graph, what that means is that we're putting bending stress on the pipe that's in excess of the fatigue endurance limit. And when we're operating in excess of the fatigue endurance limit, we're consuming the usable life of that pipe. And if we operate in that state for long enough, we eventually fatigue the pipe to failure, which is exactly what happened. And unfortunately, because they twisted off in that enormous 20-inch washout, they were unable to successfully fish and ended up losing the BHA and a good portion of the drill string and had to redrill the well. As I mentioned, this could have been identified in real time if these techniques were used as the well was being drilled. Lost opportunity, $2 million. You could spend a lot of money monitoring before you would ever exceed what it cost to twist off and lose that whole section. So I'd like to wrap up with a proposition. I have a proposition, first of all, for managers. And I've been in this manager seat before. And my encouragement to you would be, don't hire drilling engineers to do paperwork, as we tend to do right now in 2016 in the modern era. Expect your engineers to do engineering. All of the techniques that I showed, any degree drilling engineer can and should be able to do these things. And as you saw, the amount of money that's available on the table is tremendous. So it is certainly a compelling business case to have your engineers doing this sort of thing rather than filling out paperwork and going to endless meetings. In order for them to be able to do that, though, they need to be equipped with the proper software and the proper training so that they can do that job. And it's your job as a manager to allow that to happen. The other difficulty for a manager is we tend to not like to have to change things. And unfortunately, in a couple of these examples, change was necessary. Good example is number 2, where we had to change the casing. We had to drill bigger hole, run bigger casing. That comes at a cost, and we tend to be very resistant to accepting that our wells are going to cost more. But if it's what allows us to achieve our well objectives, then that cost is well spent. There's no point in drilling that long lateral if we can't case it and cement it. So be prepared that when you do this sort of analysis, physics may tell you that you need to change things. Never waste a downturn. I guess that would be my last bit of advice, is in the middle of a downturn is a great opportunity to rethink how your drilling department, how your drilling organization works. And it allows you to shift roles and responsibilities so that engineers can do engineering, and you have other folks do the paperwork and the meetings and the stuff that tends to consume the typical drilling engineer's day, so that they have time to do this sort of analysis. For educators, if any of you work in a university setting, and I'm speaking from experience here, when I studied at university as a petroleum engineer, we spent a lot of time looking at vertical wells and things like duplex pumps. We don't do those sorts of wells anymore. We don't use duplex pumps anymore. What we need to be teaching at university is how complex these modern directional wells are. And when students leave university, they need to understand the consequence of their choices. That when you choose casing sizes, hole sizes, drill pipe sizes, fluids, you need to understand the consequences and the trickle-down effects that those choices have on the overall system. So I would encourage educators to start teaching, maybe even create a class that focuses on holistic well design, designing the well as a system with the completion in mind so that we're actually achieving what it is the oil company wants delivered from this well. And my last bit of advice is for you drilling engineers out there, take ownership of the well design process. It's very tempting and easy to put the technical responsibility on the service companies because they tend to have quite powerful modeling techniques and a lot of the technical experience in their specific domain. But really, there's no one better positioned than the operator drilling engineer to understand all the ramifications of all the different pieces of the puzzle of that well design. So really, it's the drilling engineer that should be doing this analysis long before we start choosing casing points, casing sizes, drill pipe sizes, the rig, etc. All those components have an impact on the overall thing that you're trying to achieve. That is a lot of work, and hopefully if your drilling manager was listening, they're already making changes to allow you to be able to do this sort of work. Now I realize that's different than the role that a lot of engineers find themselves in. We tend to be more project managers than doing technical analysis all day long. If you don't know how to do these things, that's okay. That shouldn't be considered shameful. there's great resources out there and consulting organizations like K&M that I'm a part of that can help you with this sort of thing. We don't have to exist for the entire program. We can show you how to use some of these techniques so that you can fish for yourself, so to speak, into the future. So that's my last little bit of advice. Engineers, managers, educators, I think there's an opportunity for real change and really thinking about how we want our drilling organizations to operate. We've got plenty of time for questions, so with that, I'd just like to thank everybody for their time today, and I'll turn it over to Bernice for the Q&A session.
Thank you very much, Brandon. That was a very interesting presentation. Yeah, I would like to open now the session to questions. You can submit it through the chat box. We have some questions coming over. So the first one, how to face unexpected sudden changes in the rock lithology or pressure temperature?
Yeah, that's a really good question, and it's not a particularly easy one to address. However, in the example of that, well, that first example, although it was quite simplified, what we try to do is get an understanding with cooperation from our geologic department of what that rock strength looks like as we drill through the overburden. And if it's something that's mappable from one location to the next, we can create a synthesized expectation of rock strength for the planned well path that we're about to drill. Now, naturally, there's always going to be variations in where certain formations come in from a TVD standpoint. But if we've got that expected compressive strength overlaid on our actual observed MSE, we can start to read between the lines and see when the bit transitions from, say, a soft formation into a harder formation, and then be prepared to make parameter changes as soon as we see those sudden changes from one formation to the next. So quite a bit of pre-work is done before we actually go out there into execution phase. If you don't have that pre-work done, then you don't really know, as you're trying to apply that technique, whether or not the MSE is going up because you're drilling inefficiently or if it's because the rock strength is changing. From a pressure standpoint, there's also other empirical methods that can be used for anticipating those pressure changes. Also, a lot of LWD techniques that can be used for correlating and predicting and forecasting ahead what your pressure environment is going to look like if you're drilling, say, in an exploration area or a development area where you don't have high confidence of what your pressure environment looks like.
Thank you, Brandon. Next question would be, how important is the gauge length of the drill bit for optimal hole quality, and what should the length be as a percentage of the hole size?
That's a really good question. I am not as confident as others, perhaps, in the industry of just mandating a specific gauge length, that thou shalt always have 5-inch gauge, for example. But I would say that we've seen, and others have reported and shown quite compelling arguments, that longer gauge does tend to help inhibit whirl and lateral vibration. And what we tend to find with mechanical specific energy analysis is that it's not that common to have bit balling. What tends to be a more common cause of our dysfunction and our poor energy transfer to the bit is lateral vibration, and certainly longer gauge bits help mitigate that. I wouldn't say that the gauge length alone is the only thing to focus on from a bit selection standpoint for mitigating lateral vibration. There's other features, the profile of the bit face. There's some new technologies that are coming out that also inhibit whirl. But, you know, I think a good starting point is somewhere in that neighborhood of 5 to 6 inches of gauge length, which may need to be, you know, tuned upward or downward on the specific application. The other thing that I think is quite important is that the gauge in directional wells tends to need to either be undercut or tapered so as not to cause the trailing edge of that gauge to drag on the borehole.
Thank you. Then the following question. How reliable is the downhole torque predictions obtained from surface measurements?
That's an excellent question. We have had several opportunities on various quite extreme extended reach wells where we ran downhole torque measuring devices. And we compared that to the predictions of using this algorithm. And what we find is, by and large, the model does a very good job of predicting what the downhole torque is, as long as we have a good understanding of the borehole geometry. As we saw in that last example, If I've assumed that the wellbores gauge, but in fact the wellbores overgauge, then that torque and drag method isn't going to produce accurate results because that is a key component to the overall torque prediction. So I think the physics and the concept, totally valid. What I would caution, though, is you have to be aware of your uncertainty of the inputs, and if those inputs happen to not be what you think they are, that will affect the output. So there is a bit of interpretation that's required when you're looking at the curves, and you have to ask yourself, okay, what maybe don't I completely understand here?
Thank you, Brandon. Next question is if there is a change in the formation hardness from soft to hard and vice versa, then how do you prepare the drilling fluids? Means necessary steps?
I'm not sure I completely understand the question from a fluid standpoint. I wouldn't say that we've worked on any projects where when we transition from soft to hard rock, we do anything significantly different from a fluid standpoint. Certainly, fluid's extremely important to the drilling process. We're typically on these long horizontal wells and extended reach wells asking a lot of the fluid. First and foremost, we want it to be inhibitive when we're drilling shales. We want it to have the right rheological characteristics. But I wouldn't say that a tremendous amount of effort goes into changing the fluid from layer to layer. In fact, on long wells, that tends to become quite impractical because the volumes that you're dealing with are quite large. One thing that we do try to take into account is the impact that hydrostatic and ECD has on the confined compressive strength of the rock. So UCS is one thing. We can get that from logs. But confined compressive strength is ultimately what we're battling when we're drilling. And so we do need to look at ECD and mud weight when we're anticipating what our drilling performance is going to be through those formations.
Thank you. Next question. Drilling is a very complicated process. What do you think of using real-time data analytics to improve performance?
You know, I think that we're kind of on the cusp of people doing that more and more. And I've seen examples of folks using, you know, fuzzy logic or quite sophisticated algorithms to try to use statistics and guide us towards what are our best parameters and what are the changes that need to take place. I would kind of put that, even though it's very sophisticated mathematics, I would tend to put it more in that medicine category where we're data-driven. We don't necessarily have a model or an engine behind the scenes under the hood that's explaining the drilling process. We're just using data, which that can be quite effective. But again, I like to gravitate towards taking all that data and also overlaying it with a model. We want the physical model and the data. So I think in the future, the ideal situation would be combining both of those things. Okay, well, thank you for everyone attending. We really appreciate your time. If you have any questions, feel free to reach out and contact us. These slides will be posted to a public site where they can be viewed and downloaded at a future date. Thank you very much for everyone who was able to attend. This will conclude our webinar.